Okay, so we've been talking about electrons and where they are with respect to the nucleus, how they move and what path they are on, and that's going to be directly related to bonding and our deeper understanding of the periodic table, the elements, and reactivity as well. And so we describe these electrons with a set of quantum numbers, right? Each electron has a unique set of quantum numbers for a particular element or atom, and they cannot have two electrons cannot have the same set of quantum numbers, right? They can't be in the same position and location, same energy, right? And so these quantum numbers are, in a nutshell, and I'll talk about them in detail, right? So their energy level, for example, right? So, and we've seen that already, energy level. Are they on the first quantum level, the second, or the third? So what is the energy of a particular electron? And then the shape, I'm just going to call it the shape for now, right? So, and I drew this on the board already. Is this electron going around the nucleus like this? Or sometimes it goes around in this particular shape, right? So, and this is not flat. This is another thing you have to keep in mind, that this is really spherical, okay? It's like a soccer ball, and except much smaller. And this is more like a dumbbell, right? So these electrons fill out a shape, right? So that would be the shape. And then if it's spherical, it can only have one orientation. But if it's a dumbbell, it can have different orientations. So we have orientation. That's the third uh, quantum number, right? It can be, does it go up and down like an XY coordinate? Is it on the x-axis, y-axis, or is it like this? Or so this is the orientation. And then finally you can have up to two electrons in one of these orbits, and they cannot get in each other's way. So that's going to be called the spin, or the magnetic moment. Okay? So that's what we're looking at. We're looking at these, we're trying to describe an electron uh, with a set of quantum numbers. And so these are the atomic orbitals. And so this may be a little bit far, but we could have an electron in a 3D orbital. Okay, that would be an atomic orbital, right? And so if you remember, we had the D block and the S block and the P block. That's right, directly related from the periodic table, right? So if it's in the D block, the outer electron is going to be um, in a D orbital which has a particular shape. And then you can also an atomic orbital is basically where the electron is with respect to a particular atom, and all these atomic orbitals are the same for all the elements, but then electrons can be in different ones. Okay, so here are the four quantum numbers. Okay, N, L, M sub L, and M sub S, right? So principal quantum number, energy level, like I said, the energy. The second one is angular momentum, or the shape, right? Does it have an S shape? We have S, P, D, F, all kinds of different shapes. And I have pictures of these that I will show you that are quite interesting. So for now, like an S orbital is a sphere, a P orbital is a dumbbell, and then what direction? If it's a dumbbell, we can have three different P orbitals. Is it in the PX, PY, or the PZ orientation? And then spin is spin up and down. That's either, if it's in an orbital, all we say is it going against it or towards it. So up or down. We're going to say plus a half or minus a half. All right, so let's back up just slightly here, right? So the principal quantum number one, the energy level, right? So what is the energy level of a particular quantum number? And they get whole numbers, right? Because we already know that these quantum numbers, that's the name, they're quantized, meaning they can either be 1, 2, 3, or 4. Those are the levels. There's nothing in between. They're either on the first level or the second level. And so they get this as n equal to 1, 2, etc. Sometimes these, and these correspond to the shells. They are, the K shell is equal to quantum level 1, K, L, M, N, O, P, Q, R, right? You follow the alphabet. L is quantum level 2. And so this is directly correlated in the periodic table. So, oh, where's my periodic table? Let me go have one right here. Okay, so the periodic table, and I'll go back to the other slide here in a second. So the periodic table is exactly oriented like that. So this is n equal to 2, right? So this first period, where did it go? This first period here represents the first quantum level, and then this represents the second. So you see on the first you can have 2 electrons, right? So n equal to 1, and then this is n equal to 2, right? And so n equal to 1 can only be in an s orbital. Okay, and so this is why this is in the s block. And so unfortunately this is a little odd. This is over here in the p block, but their second electron, there is room here. So sometimes you also see helium on the left side here. Electronically it fits in over there on the left next to hydrogen, but reactivity wise it has a full quantum level, right? So there are only 2 electrons that fit on that quantum level. And then the third quantum level goes on the third electron goes on the third quantum level, n equal the second quantum level. Right now, the third electron goes on the next level, which is of course the second one. So this would be n equal to 2. Then this is n equal to 3, 4, 5, 6, 7. Okay, and then there's some exceptions, not exceptions, but there's some discrepancies here, which I will point out to you slowly, right? And so you can actually put up to 8 electrons in there. 2 can be in an s orbital here, right? So this is the s block, remember. So the third and the fourth electron, but the fifth then is still on the second quantum level, but it goes into a p orbital. And if you remember that we had 3, we had the px and the py and the pz, right? If this was an x, y, z type coordinate system. So you can put up to 2 electrons in here. So this is why there are 6, right? So px, py, and pz, although we don't know which is which, right? So the first electron that goes into a p orbital can be in the px, py, or pz. It depends. And then the third quantum level actually has 18. Okay, they can have an s orbital, and they can be in a p orbital, and they can also be in a d orbital, right? And so although this is not in the third row, this is actually the third quantum level, and that's where things get a little weird. And then this is actually the fourth and the fifth. So after the sixth quantum level here, the fourth one. And so you need to just kind of remember that this is where the 3 is, and this is where the 4 is. So you got to remember that this is all inserted. This will make sense later on. All right. So here we have the shells, K, L, M, N, which correspond to quantum level 1, 2, 3, and so on and so forth. And if you square that, you can calculate the number of orbitals, of total orbitals that are possible on this particular shell, right? So n squared here is 1, so we can only have 1. And as we said, that's just the s orbital. The first period just has hydrogen and helium. The second period, n squared, is 4, so you can have s and p. And then the third one, as I pointed out to you, is not just s and p. We also have here that third one. So those 10 electrons are part of that, which makes it then 18. And then 4 is 14. So now we have f orbitals, and so there are 7 more here. Right? So if you count that, there are 7 more that are inserted. So on the fourth quantum level, you have S, P, Ds, and Fs. And if you wanted to calculate the number of electrons possible to be held in, let's say, n in the third quantum level, you would do 2n squared, right? So n squared gives you the number of orbitals, and there can be 2 electrons per orbital. So there are 18 electrons total, which is what I've been talking about. 18 elements are part of the third quantum level. 4 atomic orbitals are present for the second, n equal 2. There are 4 orbitals. This would be so much better if you were in the classroom and you could yell at me. Orbitals, right? but each orbital can have one, so we have 8 elements here, right? 1, 2, 3, 4, 5, 6, 7, 8 in the second period. So that was quantum level, quantum number 1, and n which is equal to 1, 2, 3, 4, 5. Okay, so L is the angular momentum. What kind of shape do we have? Okay, and so L is S. L equal to 0 means it's an S orbital, and so the for n equal to 1, we can only have a possible L value of n minus 1. That's the highest possible L value. So for n equal 1, we can only have an S orbital, or L equal to 0 here, okay? And so so that's just one orbital. And so for n equal to 2, we can have n minus 1, which is, so L is equal to 1 or 0. So for second quantum level, we can have electrons in an s orbital or a p orbital. And for the third, we can have them in an s and a p and a d. But the highest possible one is the d. And so, and this here, 2L plus 1 gives you the number of orientations actually. So that actually gives you already m sub L, which is on the next page. 2L plus 1. That tells you the types of orientation. An s orbital can only be an s orbital. A ball is just always going to have the same direction. And that would be quantum angular momentum, or L. I'll call it the shape, but it's angular momentum. And so here we have, looking at 3 different s orbitals. Okay, the 1s, the 2s, and the 3s, right? They all are spherical, but they are further and further apart from each other, right? The electron on the first quantum level is close to the nucleus, and then the second one, the higher one, the 2s, is also going to be, think about if we have potassium, there's 1s, 2s, 3s, and 4s. So we have 4s orbitals, and a total of 7 electrons actually in s orbitals. They're just have different quantum numbers, or different energy levels, right? So the first one is here, and the second one has to be further away, and so there are these dividers there in the middle, so they don't interfere. So there's this area where you don't have any electrons at all. Those are called nodes, and this is what's if you look at the 3s here, right? So we have 1s, 2s, and 3s here, right? So 1 is all, but this is 2 and 3. We wouldn't have anything here in this tiny little divisor, and so this is called a node, and this is what you see here, right? The probability of finding an electron is 0 when it hits the baseline here, right? So we have 2 nodes here. Of course, at the nucleus, we also have a node, an area of 0 probability of finding an electron. This just shows you that the 3s orbital, most of its electron density is going to be further away from the nucleus, whereas the 1s is going to be closer to the nucleus. And then, so this at point 1, which is here for the 3s, you have a little bit of residual electron density, but most of it is further away here, right? Okay, so that would be still L, for L equals 0 for the s orbitals, and having different kinds of quantum, energy levels, n equal 1, 2, or 3. This is a contour, a cross-cut through an s orbital, right? So 1s, the darker the purple here, the more likely you have that electron density. So it's just like it's here, and then it thins out a little bit further away. Whereas the 2s orbital, you've got your electron density in an outer ring, so it's almost not spherical, but it's more, yeah, it is, but it's hollow in the center, and so it really and you got to remember, this is just a crosscut, so you get a 2-dimensional idea. Now here's your 3-dimensional idea, right? So the 1s orbital is really a ball, and the electron density, and the second one is further away. This is what a p orbital looks like, and I have some other really nice pictures. The Tro book, the book you're supposed to be using, has some really nice artwork in it, especially in this chapter, and So this is a p orbital here, right? So you can have this dumbbell or peanut if you wish, right? So this is just a cross section of electron density. Most of it is concentrated here, and then you got a little bit further away. But and so you can have three different orientations, and that would be m sub l. Okay. The d orbitals. Okay. There are 5 different d orbitals. They have very interesting shapes. If you look, consider a XYZ coordinate system. It's the x squared minus, oh, they're not, yes, it's the x squared minus y squared. And I'm looking for it because this isn't it. The x squared minus y squared is directly on the axes. Oh, okay. It's really hard to see, right? It looks like this is like a dumbbell, but it's not. It's a peanut, and so let me relabel this coordinate system, right? If I make this x and y, not this is x and this is y here, right? And if I made z here and I drew the x squared minus y squared, the electron density would be directly on these axes. And so this is how you can remember the designation of these d orbitals. And then you have the dz squared, which is the other axis, the z axis, that is directly overlapped. But it has that donut component to it, which is kind of weird, right? So there has to be a second region where the second electron is, and that's there, and then all the other ones are in between, right? So the dyz here, if I put it down here, it would be in between these axes, right? And so you have 3 orbitals, the dxz, the dyz, and the dxy, that are in between here. Again, it's hard to see, but this may give you a better idea. Okay, so those are just the shapes. For you right now, focus on just understanding that there are 5 different d orbitals and that it can hold up to 10 electrons. These are the f orbitals, okay, and so there are 7 of them. They look quite bizarre, but just so you have seen them before, and as I said, they're rare earth elements. We don't really get to work with them all that much, and you won't in this class. So as far as the third quantum, the magnetic quantum number m sub l, the direction, is it x, is it y, is it the px squared, the dz squared, or the x dz x, or whatever, dxz. You can calculate the number of orbitals, and so they could just go from minus L to plus L, right? So if you have a p orbital where L is equal to 1, then the 3 magnetic quantum numbers are going to be minus 1, 0, and plus 1. We don't distinguish x, y, z because we actually don't know. We just know that there are 3 different orientations. And d orbitals for L equal to 2, we know we have 5. So the m sub L, right, that's the third quantum number, is going to be equal from minus L to plus L. So it goes from minus 2, minus 1, 0, plus 1, and minus 1. So, this could be the x squared minus y squared, or it could be the dz squared, right? So we don't distinguish when we just deal with quantum numbers. And all right, and so we know this is reflected in the periodic table here, right? We know that there are the d orbitals 2, 3, 4, 5. There are 10 different elements here. That means it has to accommodate 10 electrons, and since there can be 2 electrons per orbital, this is how we know this. This is an electron that's of course, chromium, for example, has 24 electrons, so they can be, and so the highest quantum level, energy level, is equal to 3. So we can have n minus 1, we can have L equal to 0, we can have L equal to 1 or 2, so we can have S, P, and then D. and we can have different orientation. So it depends on what orbital, what electron exactly are we talking about here. Is it a 1s orbital electron? Because we have those as well. Chromium has 1s, 2s, 3s, even 4s, and then 3ds and 2p's and 2p's and 3p's. So there's a ton of different electrons in here. And the final spin quantum number is m sub s. It's the magnetic moment. It's either plus or minus 1/2. Sometimes you even see this left, but so m sub s is always, no matter what it is, it's either going to be plus or minus 1/2, one or the other. Right, so that if you have 2 electrons in an s orbital, if you have helium, there are 2 electrons in helium. They're both in a 1s orbital. One has to have spin up. One has to have spin down, or they can't exist with each other. All right. Again, this is just kind of a mini summary here. S orbitals are spherical. P orbitals are peanut shaped, and d orbitals for the most part are propellers, and we don't even have the f orbitals here listed. But L equals 0 always means s orbital. This is a summary of all possible permissible quantum numbers here. All right, like I said, if you have an element that has quantum number 3, any of this is possible. Anything this and lower is then possible. Like okay, well, this is in just a 3s, like potassium. Sorry, let's say sodium. Sodium has 11 electrons. Sodium is could be a 1s, could be a 2s, could be a 2p, or a 3s, or a 3p, not potassium. Then I have to have gallium or something. Anyway, more importantly, you should be able to tell me if some of these are permissible or not, and why. Like a set of quantum numbers, like an electron here, and you want to find the problems, right? So n equal to 1 means the limitation for L is going to be n minus 1. So the highest one here is going to be 0. So this is okay. And then m sub L, if 0, then 0, that's fine. Plus 1/2 and minus 1/2, so that's fine. That works. This one is possible. Here we have a quantum level 4. We can have L as 3, 2, or 1. That's fine. If it's 2, m sub L can be from -2, so -1 is perfectly fine. And plus 1/2, so this one looks like it's doing okay too. N equal to 3, L can be 2, right? Anything m minus 1. And again, so it doesn't look like, so far it doesn't look like we have a problem, but this is okay too, right? And so this is going to have to be it. Let's find out why. N equal to 2, and here's the problem. If n is equal to 2, L can only be n minus 1, and so 2 is not permissible. So here's your problem, right? Because if you have L equal to 2, this is still possible. Okay, and then finally, I may ask you something like this on an exam. Find the possible values for all 4 quantum numbers for an electron found in the following orbital. So now I'm asking you what the set is for a particular electron in an atomic orbital, right? So you get everything from the 3D here, right? That means n is going to be equal to 3, right? N is always going to be equal to that number. For D, you just have to remember S, P, D. S is 0, P is 1, D is 2. So L is going to be equal to 2. And then M sub L is always going to be minus L, which in this case, oops, that's a 2. It's going to be minus 2, minus 1, 0, plus 1, and plus 2. And then M sub S, I want it. It's always going to be the same. Plus 1/2 or minus 1/2. 4s, n is going to be equal to 4. All right? and I'm asking specifically for s, so it's not n minus 1 in this case. Yes, n minus 1 is possible, but this electron is in an s orbital, so L is going to be equal to 0, and m sub L is going to be equal to 0 as well. And then m sub s is going to be equal to plus or minus 1/2. For F, n is equal to 4. L is going to be, if it's in an f orbital, is going to be equal to 3. And then I'm going to run out of space, but m sub L is going to be equal minus 3 minus 2 minus 1, 0 plus 1 and plus 2. See, an f orbital has 7 different orientations. 1, 2, 3, 4, 5, 6. What did I forget? Oh, plus 3. Well, it's a good thing I checked that, right? It goes from minus L to plus L. So we go from minus 3 to plus 3, which makes it 7. And then m sub s equals plus or minus 1/2. And finally, we have, I'll write it over here, a 4D orbital. N is equal to 4, right? That's just equal to that. D, this just, you got to memorize. N is going to be equal to 2. M L. M sub L is equal to minus 2, minus 1, 0, plus 1, and plus 2, the 5, and then m sub s, as always, plus 1/2 and minus 1/2. And this is the end of chapter 2, and now you have to take an exam. Woohoo!